So I will just like to highlight, like, when you are doing the analysis, before after analysis, you have to also understand what time period you are considering, and any graph that you have generated, what does that represents. Let's say 15 minutes, half an hour, or you can have an analysis done over a specific time interval but over multiple days. So they represents different variability. The variations you are observing here is the variations within a specific cycle. Variations you are observing here is the variations over multiple cycles, and variations you are observing here is the variation over multiple days. So whenever you are generating your or doing the before after study or generating your plots, you should tell how they have been generated, because the more, like, you should explain how that what process you have followed. We talked about cumulative distribution. I just take one other slide from my pack, that let us say if you have a travel time values, like these are the travel time values, and the cumulative distribution is basically giving that the empirical probability density function of that travel time values. I have just taken 4 values here, and it represents 25th percentile, 50th percentile, 75th percentile and 95th percentile. You can get those things from the empirical probability distribution. Now moving back to this one, I will have data from different sources or different time periods. I can have a data for a specific day, day 1, and day 1, what I mean is, let us say day 1 over, let us say that 11 to 12 we were discussing 1 hour of time interval for different cycles. So I can have a data for day 1, data for day 2, data for day 3, because each data point will have its own spread. And I can, when I am drawing my, I do not know why this, okay, when I am drawing my cumulative distribution function, I can consider all the data sets I have and I will get one shape, or I can take a mean of each days and look at the CDF plot, I will get some other shape. So they are 2 separate distributions. When you are doing a before after analysis, you should be making sure that the way you have analyzed before is the same way you have analyzed afterwards. Do not do that mistake that somebody has given you one curve before and you have generated another curve afterwards, and you do not know how that curve was defined beforehand. If I say this is a representative for that day, then the distribution of this one is representing day to day variations, whereas that all data set, it can happen, let us say one day you have more data, other day you have less data, has some biasness attached to it. But generally you will never have too much data for a single day if you are using, let us say, a Bluetooth or the vehicle trajectories. You might consider all of them to generate your plot, but be consistent in your before after analysis. As I said earlier, data source and the data methodology should be consistent and should be documented how you have done it, because if you have said I got a distribution like this today, after 1 year you again get another distribution and you like to compare, oh, how was my last year compared to this year. If the process has changed, that comparison is not fair. Does that make sense? Okay. Other thing I talked about was the reliability indicators like buffer time index or planning time index. If I have, let us say, a distribution of my travel time, this is the x axis is the travel time, y axis is the number of observations. So this is not the cumulative distribution. Cumulative distribution is summing up all and getting a curve. This is just a distribution. You have a mean travel time, let us say mean travel time, please do not worry about 8:45 minutes, it is 8.45 minutes, right. There was some error in that slide, but anyways it is sorry, this is a mean travel time, yeah, let us say it is 8.45 minutes. Buffer time from here to there is 2.45 minutes. So this is the 95th percentile. So the buffer time represents, on average, if it takes you 5.45 minutes to travel, you need to have 2.15 extra minutes, so as to be confident that 95% of the time you are going to reach on time. So that is the buffer time, the extra buffer you have to consider. So when you say this buffer time, 95th minus mu, or buffer time index 95th minus mu over mu is the average, it is telling you this extra buffer you should have in your pocket when you are traveling. Similarly, planning time is, if you say my actually planning time is 95th percentile over free flow, it is actually representing this 95th percentile 8 minutes, free flow might be, let us say 2 minutes, 8 by 2. Do not worry about the values here, because this graph has its own noise. I just grab it from one of the students' presentation, it has noise, but I want to just tell you how it looks like, right. So, it tells you that, okay, the distribution is known to you, the buffer time is the extra time that you have to consider. Yeah.
So, number of trips in the free flow condition we can reach within 2 minutes.
Yes.
The congestion
it takes more than 9 or 10 minutes. This is 10 minutes. Yeah. Then the two strategies, curve 1, curve 2, both of them are giving you more or less the similar means. The means are same, but the blue one is having less spread. So, blue one might be a better strategy compared to the orange one, right. Does that make sense? Yeah. So, that one, the one I was just trying to, I will skip all these ones. I just borrowed some other slides to just discuss that part. So, we were discussing about the vehicle, sorry, we were discussing about the split failure. Just quickly again revise what we discussed, and we are talking about the vehicle trajectories. We showed you these trajectories. In fact, this data set comes with the it also differentiates with respect to what type of vehicle it is. So, when you have that data set, it can like your connected vehicle data gives you far more detailed information. But you can, if I zoom in this portion, that is how your trajectories looks like. So, these are the points you have observed. Obviously, this one might not be a split failure, because it looks like it is hitting during the green time, but red time, but actually you have to consider the actual profile based on the shock wave or other aspects, because there might be a shock in the system, and like you have to basically just do not blindly use it. So, for your trajectories you really need to have a good number of sample, and you also need to have more frequent observations. That is your requirement. Like this one definitely is the green one, where the other one was not. I mean, this student basically was working on applying the shock wave theory to give a more better shape, but you can basically think of integrating different concepts together to further redefine your trajectories that can help you to make more that can help you to have better accuracy in your estimation, whatever you are estimating. So, now other thing which I want, yes.
Sir, does the points indicates a red, stop?
No, this indicates red means signal red.
No, sir.
These points.
Plot,
yeah.
Small points are there.
Dots. So, GPS coordinates might be, you are getting a GPS coordinate, let us say every 5 seconds, 10 seconds, there is some frequency you are getting. So, you got one point here, other point there. So, that is not like it's just a certain frequency you might be getting. So, these dot represents for which you have the observation, and then you interpolate between the two by straight line, right. So, you want to have more frequent observations, so that you can have a better trajectory defined. So, in this case, so actually the one he interpolated, but you want to have more frequent, so I can have better definition of my trajectory. Maybe the trajectory here was perhaps whatever it was, something else, right. So, you need to have more frequent observations, then you can figure out if it is more than one, or if it is more than one stop or not. Now, we discussed the split failure thing. So, if I go back to the split failure concept, just to revise it, we discussed about the split failure concept. Vehicles are having a good green I would say flow, but they are stopping twice and they might be hitting the red. So, if they are stopping twice, then they will be hitting the red in the early time periods of red, right. And we said, okay, if I have a okay, where was it? Okay, just later on. I can have a condition like this where the green is well utilized, but the red early red is also occupied. Here the green is not that well utilized, red is also will not be well occupied. So, if you have a data set that can help you to identify the occupancy during the green and the occupancy during the early red, then you can be, do you think you will be able to make some guess or some estimate of whether there is a split failure or not. So, in this particular case, you will be like you will have almost close to 100% occupancy for the red, right, high red occupancy, but in the first few seconds of red you will have some amount of occupancy also. Green, you will have occupancy based on the saturation whatever you are expecting, a very good saturation occupancy means you had a good flush happening. So, you have some occupancy during green, and the early red you have high occupancy also. So, you might have a high occupancy in this case for green and red. Here what do you say? Do you have a good occupancy for green and good occupancy for red? What occupancy you will have for red? Yeah. Yeah. So, you are talking about, okay, I forgot to mention this is a stop line loop detector, detect the stop line. Okay. So, in this period what you are saying is you will have some you will have one pulse, another pulse, no pulse, right. What about here? All pulse, right, all pulse, 100% occupied more or less in this figure, right. What about here? No pulse, not occupied. So, you have a, if you look at this green and red together, almost 0 occupancy there for the initial red, in fact 0 occupancy, some occupancy in the green. Yeah. So, that is an interesting thing again. So, in other words, in fact we have discussed about the occupancy. If I look at my green time, you have a pulses. So, you will obviously the percentage of the time my green was occupied is your green occupancy. So, if the traffic is flowing, this occupancy will be a high value, maybe 70, 80, 90, right. But if I say this time is my red time, do you expect this kind of pulses during the red time? Stop line loop detector please. No? Why? Yeah. Yeah. If this thing is happening, then the drivers are not respecting your red light, they are just entering the intersection. So, you are during the red time, we do not expect red time, it might be, if this guy has arrived, it should be 100% after that. It stopped and go, right, you will have high occupancy. So, if the vehicle, so the first time you have a pulse of 1 represent the time when the first vehicle has arrived. So, if I look at the initial certain time periods of my red, that occupancy will tell me how quick that vehicle has arrived. So, what we do here is we define two terms, green occupancy during green, GOR, green occupancy ratio, which is the percentage of the time when the green was occupied, and occupancy during red, I will not be focusing on the entire red. I know that after a while somebody will come and stop at the intersection. So, I will not take the whole red, I am only going to take the first 5 seconds. You can take 5 seconds, 3 seconds, 2 seconds, whatever you specify, do not go for a long, right. So, GOR, ROR, I am going to say the ROR, let us say ROR 5 is the occupancy during the first 5 seconds. So, if I go back to this is my first 5 seconds, then whatever occupancy we have observed in the 5 seconds is your ROR. So, which is the time when the detector was occupied in the 5 seconds. Please keep this in mind, it is not the whole for the red, right. So, I have two different values. So, I mean this one was just to show that okay, there should be a high red occupancy, that is fine. So, when the vehicle is discharging from the queue, we know that this is a split failure. In this particular case, we have defined that this is not a split failure, because the vehicles are, so sorry, when the vehicle, when you have a split failure, definitely you have a high GOR, high ROR. ROR is the red occupancy ratio, GOR is a green occupancy ratio. You will have high in this case. In this case, how is your GOR and ROR? In this case, high, both high, right, the first 5 seconds. Here also, do you have a high? ROR, GOR is less, ROR will be high, right. The vehicle hits during the let us say the first 5 seconds, ROR will be high. So, the concept here is, if I plot my GOR and ROR, the green occupancy ratio and the first 5 seconds of ROR, in literature they also say ROR 5, means just to highlight that it is not the red occupancy for the whole time period, it is only for the first 5 seconds. Then if you think of a thresholds, this region where you have a high GOR and high ROR, there is likely that there is a green split failure. It is possible that there is a split failure. Yes. So, if you plot your GOR and ROR values from a stop line loop detector, start plotting them in this region. If you have too many data points happening in that space, there is a possibility that there is a split failure, and for one approach, by the way, not for all the approaches, right. This will have separate approaches or separate phases. Does that make sense?
Maybe around 4 to 5 seconds would be
Because after 5 seconds, if somebody else is arriving, it can be because the traffic has to come to the intersection, right. We define the split failure when you have to stop for twice, not once. If you have to stop, if you are stopping more than one red light, then it's a failure. Now, let us have some use case. What can you say about this one? High ROR, low GOR. About this one, high GOR and no, high GOR and high ROR 100% occupied, right. High GOR, right. When can you observe this kind of behavior? Sorry? Huh? Yeah, ramp, yes, no, ramp, okay, you will have one vehicle leaving, but on the intersection, think about you are approaching intersection, signal is green, but you have to stop. Emergency can be one, yes, breakdown can be one, or there is a spillover from downstream. The downstream has spillover, you cannot enter because there is no space for you to enter, right. So, it is not a, if this case is a spillover from downstream, this case is a bad coordination case. You are having a high ROR, but a low flow is a bad coordination case. If you would have done a proper coordination, you would have been able to spill the, you should have been able to flush the vehicles. That case is a spillover case. But what can you see from this? Like in addition to GOR and ROR, and you have a stop line loop detector, only detectors at the stop line. Okay. Can you, if I give you a GOR and ROR data, can you add one more check on it to differentiate these cases from your split failure? Very high case, yes. So, if you 100% GOR 100% ROR can be neglected, maybe because of spillover, yes, that is possible. But imagine you have some vehicle arriving here, imagine this way, instead of showing this way is going that way. So, you arrive, you stop. So, you have a still some GOR and you have 100% ROR. So, you still have some GOR. In this case GOR is 100%, but you still have, let us say, less than 100%, maybe 50%, 60, depending on what time of the green you have arrived, right. So, how can I differentiate my spillover from there? How many vehicles have been served in the first case? No, 2 for the green, yeah, first case 2, second 3, you have counted both of them, that is fine. So, first case 2, second case 3, right. In the, if it was a good no spillover, so if there was no spillover, you should have been serving vehicles, right. So, if there is a spillover, your serving is quite low from the stop line. Said you only have a stop line detector, you do not know anything beyond that, only a loop detector at the stop line in this case. So, what we can say is, on top of GOR and ROR, I can also have a demand served over the capacity I have specified, a third dimension to it. If I have that, a high GOR and high ROR with a low demand. So, high GOR, this axis is GOR, this is ROR, and that is a demand axis. High GOR, high and low demand is perhaps a possibility of a downstream spillover. Possibility, right? There is a possibility that there is a downstream spillover. Obviously, high GOR, high ROR, high demand served is a split failure, definitely. I will be more confident. And then you can think of other combinations. So, what I want to highlight was, yes, if I go back to this image, I will have potential split failure points, but I will also have potential those points also where there is a spillover from downstream. So, this spillover from downstream means I have to make some improvements in my downstream intersection to avoid that spillover, right. So, my intersection I might have given a good split, enough green, but unfortunately the downstream is not able to serve properly. So, the problem is further downstream, fix that problem first, then only I can fix here. Yeah. So, this is more about looking at your data set, coming up with some sensible way of identifying the issues in the system, and that can help the agencies to identify, okay, yes, there is some issues. So, think of these algorithms running at the back end for the whole network, and then telling though, look, these intersections for these time of the day, these are the potential issues in the system. So, you have the vital sensors attached over the whole network, data processing is happening, and the sensors are telling that there are some health concerns over your entire traffic signal system. We also call them as, like in our team we say that we are basically monitoring the health of the entire system. You have a data set, just monitor the health and tell them there can be some issues that should be addressed, and that can help the engineer to actually have some more informed more informed support, so that he or she can take a decision. Yeah. Does it make sense? Now, that was for this I would say ways to present the information. I will not like to just quickly present another interesting thing that we did long time ago, was focusing on emergency vehicle preemption. We did not develop that algorithm, but we wanted to see how we can present that information, that that if there is some emergency vehicle preemption happening, how does the signal react to it, how does the signal behave to it, and how we can present that information. So, I am going to just show a graphical way. If I give you a traffic signal timings, how you can graphically represent that during the time interval to understand the emergency vehicle preemption behavior. Emergency vehicle preemption means EVP we call them. There is a difference between preemption and a priority. Priority means, let us say there is a public transport priority, you want to give a priority to the bus as the bus is approaching the green, approaching the intersection. So, you want to give a green to him, but that is a priority. Even if you miss it, it is not a problem. Preemption means you have to do it, you have to give a green to that one. So, you will override other things and force yourself to do that one. So, that is what is meant by preemption, because in emergency every second counts, you really want to let it flow, you do not want to hold that vehicle. Now, there is an algorithm that Department of Transport and Mains Road has done an excellent job here by engaging both local state roads plus by the local government and the state government together. So, the whole city of Queensland basically at certain points, both of them are following the EVP system. So, whether it is a streams system managing the arterials managed by the Department of Transport and Mains Road, or it is a SCAT system used in the Brisbane City Council, EVP has been forcefully implemented in them, because when you want emergency, you want to give the priority. So, when I said in the beginning that the different departments do not talk, but for high end things they have to join hand together. Now, I am just giving a conceptual way of how it works. Whenever there is an emergency call, the emergency vehicle is about to leave, it sends the information that I have to leave now, the routes have been specified, this is the route I might be following. There is an algorithm that defines expected time of arrival of that emergency vehicle at a specific intersection. So, if this is the intersection, it knows that by this time I am expecting an EVP, and this time might be updated on the fly. It is not a fixed static time, because as you are moving it is going to change. I have my own plan to follow, my tone signals to follow, right. So, what I know that before this thing happens, I need to have some flush time, any queue in that approach should be flushed. So, definitely I have to make sure that I will intervene the phase needed or phase requested by that emergency vehicle by this time. So, if this thing shifts, this thing also shifts. So, you will have some flush time, because you do not want an emergency vehicle to come and join the queue, you want it to be flushed. Then you might think of, if I am somewhere in this region in my current time, I still have a scope to follow my current signal plan the way it has been designed, because you do not want to disrupt your system too much. So, this is the time, if I am here I can still work around, and obviously there should be a minimum green I will be specifying to a specific approach, there will be also some clearance time I will be specifying. So, you have some buffer attached to it, and these are the parameters for your EVP enforcement at the intersection, and that is how you will define it. So, if you are approaching here, if you are somewhere in this region, let us say you have been requested to call a phase D, that the phase D has the respective movement that emergency vehicle has to follow, and you are somewhere here, you do not have enough time to run any other phase, you will straight away go to phase D. You are somewhere here and you have a time to run, you will choose whatever that run was in your plan, you will run that one and make sure that you have that cutoff done before this time interval. So, the concept is not very complicated here, right, and you just code that, fix it and make sure that it is going to work that way. So, one thing that actually we were doing was we want to study, okay, yes, that is a corridor where emergency vehicle is running, the algorithm was defined. So, this whole thing was done by the engineers at the Department of Transport and Mains Road. They implemented it into the system called streams, the one that we discussed. Implementation done, and you would like to see how well it is behaving. Can I really see, yes, it is behaving the way we have defined it to behave, but these are hard coded in the system. So, we wanted to present it graphically. So, this is the way we decided. What we did was, we look at the corridor, we define our time period where we have cameras, EVP, etc. Right, we identified those intersections, took the data from the camera, identified whenever the EVP came and cross verified it. But what I want to highlight here is the way to present the information. So, what we are presenting here is this is a time, that is the signal cycles. So, it is like this, a time 1, 2, 3, 4, this whole time period I had a phase A. So, we had different colors, phase requested by emergency vehicle, end of phase, EV accepted, EV running, ETA, EV termination, and so on. So, this was phase A was running, phase B run, phase C, phase D, so on. This is working fine. That is your second phase, second cycle, that it goes up, third cycle, and you can see that there are, the cycle is pretty much constant here. Then when you are in this cycle, at this point, EV was accepted, I guess, at this point, and the phase was requested was D. Now, the phase requested was D, and you are already in D, you extended that until the EVP has cleared, and then you terminated it. So, again so you can easily see, yes, my EVP is working fine, the algorithm was okay, and then you have B, again ABC and so on, and then there is some recovery algorithm, you want to recover back. So, they had an algorithm to do that recovery. You can see after a while they have a slightly modifying cycle, you want to come back to the cycle as early as possible, especially if that corridor is coordinated. That is one example. Another example, you have a phase A, B, C, D, E, F. Phase A was called again in the cycle sequence to serve EV, and a phase F was shortened as compared to the previous cycle. So, at this point of time you got a request accepted that okay, yes, I need to call a phase A. So, you are at A, B, C, D, you have enough time to serve E, and then you called A again in the cycle, then you served the EVP, and then you have enough time to serve F, you served F, and then you started your cycle again. So, in this case you have called another the phase A again. This one is another example where the phase B was called. So, extending first occurrence of B till ETA would have resulted in extended green time for phase B beyond allowed maximum green time. Also, there was enough time to serve the phase D. Now, these decisions were made by the controller, that when we extracted, we studied, and we want to figure out what is happening. We found that okay, this is the time when this is the ETA, EV was accepted, ETA was perhaps somewhere, I do not know where, it must be somewhere here, EV, so EV was terminated here, ETA was somewhere in this. So, this was the expected time for the EV to arrive. So, you were at phase A when you got the call. The next phase was phase B, you did not extend phase B, you still served phase B for a while, then you went to serve phase D because you had enough time, but then you stopped D and you started serving phase B. So, these decisions are made by the controller to give emergency vehicle the green phase, but I am just trying to show you different ways of presenting the information to and to actually cross verify that yes, whether my system is working fine or not. Another example, and so on. Any question? Yes.
After a cycle has ended once, you again initiate the same cycle, right? But at different intervals.
Yes, like for example, this gun got end at E, start A, and so on. So, you start. So, when you finish at D, it has to start with A. So, it all depends on the configuration of the intersection. A is always the first one to start.
But it looks like you can actually invoke that when you get the call,
Mhm.
at the controller station, right? They will receive the call.
Yeah.
And they can initiate that sequence.
It's automatic, everything is automatic. Whatever I am presenting is automatic way of doing it, there is no somebody manually doing it.
How do you receive the request that we have?
Oh, that was the message sent by the, so emergency vehicle message sends to a control center, that sends directly to the, because all these intersections are connected, they are connected to a server, like you are able to see, I was able to see the whole intersection. So, the messages was sent to them, look, this is an ETA, that is the phase I am requesting based on my expected route. So, that is the information the controller has received. So, controller received or accepted the information at this time, for example, in this case, or actually in this case it has received the information, for example, if I take this one, has received the information here, he got the information and I said, okay, now I got the information, your ETA is here. So, I will make my decision now, the controller is going to now make the decision what to do, and the controller knows the plan, like you have seen that actually video, it knows the plan what to select, and it also has the corresponding demand. So, the controller decided to serve B first because it is very close to B, serve B, then terminate B and start D. I mean serve B, start D, and then make sure that you are starting B again. So, you have called the B phase again. So, sometimes when you are analyzing your signal and you are saying, oh, my phase was called again, if you do not know that EVP was implemented in the site, you might be wondering maybe why this thing is happening, why this. So, those things are happening because there are some overriding functions being implemented to make sure that we have a preemption for emergency vehicle.
If they are aware about these systems, the people are behind, they are working, they are aware.
Not too much. I was not aware of these systems, but public is very mindful of emergency vehicles also.
Emergency vehicles, signals are being controlled and optimized.
Also, to certain extent they are, but public is always unhappy about signals, no matter whatever happens. Signals and public transport are two things you are never happy about it, I mean most of the time. But yeah, they know that we have automated signals, we have loops and all those things, but they are not properly retimed that for, and then public very quickly give a call, my signal is not working well.
Sir, since this is fully automated,
Mhm.
what is the backup scenario in case of any cutoff of?
Oh no, all intersections have a fail safe model always. Something goes wrong, it will always have a plan that is going to run on. Always, you will always have some fail safe attached to that one. If something goes wrong, this is what I am going to do, and that has been specified, that is always there. So, now let us discuss about, we have talked about a lot of cars and all those things, and I said also there is a lot of interest nowadays, not just focus on cars, focus on the mobility of the people, focus on sustainability. And if you look here, my signal can be smart only when I am focusing on the mobility of the people and goods, not just the mobility of the cars, right. But no matter how smart, how good algorithm I make to control my traffic, right, I can come up with a group based controller with a qubit with the max pressure working very fine in the simulated environment, I can do that. But if I am not able to detect them, their smartness will go away. So, this is a very important thing, that detection, sensing and perception is a very important thing, and that is what you have always said when I ask you about Indian condition, we do not have a data set. What can we do? We do not have a data set, that is what you always raise. So, this detection is very important. Here the question is how do we raise the data, there the question is how do we get the mobility of the various road users. So, detecting, sensing and perception of traffic and road users is very vital. No matter how smart the traffic signal control logic is, it cannot detect the user, it cannot take an optimal decision, that is the foundation. So, if I look at an intersection, this is a big intersection, you would like to detect at the, right now you are detecting at the stop line or slightly upstream depending on what you have, definitely you would like to detect that. There are different type of detection systems, you can have a mid or advanced detection, or you can have a queue detection based on cameras etc., which can give you some information. You also need to detect your pedestrian movement or your cyclist, right, you need some sensing technology to do that detection, and obviously you also need to detect your cyclist on the road, not just you know on the footpath. Plus you want to give a green wave, you should know how my progression is happening along the corridor. So, there is so much need for detection at the signalized intersection. We have already seen this slide, detection and sensing technologies has been there for long, loops are inductive loops are well matured, well accepted, and there is a lot of interest in the non-intrusive technology, that you can have a visible light cameras, thermal image, radars, lidars, hybrid, that can be utilized for controlling various things. So, we did a project for the department to study the improved sensing for signal intersection. review, we did a lot of survey. We went to various vendors to understand their technology. We asked them to give us contact of the places where the technology is implemented. We interviewed those guys to understand how well the technology was, etc. A lot of things were done. I cannot present everything here, but what I am highlighting here is, and there is a and the public report is already out, and you can find it on the iMove website. But it doesn't contain any sensitive information. It's just whatever findings we had. Now we found that at least in Australia, loop remains to be one of the preferred choice of practitioners because of its reliability. They understand the data very well. It has been there for last so many years. It works so well, whether it's a rainy, it's a snowy, it's a foggy, it's like X, Y, Z, whatever thing, all the environmental factors, it is giving you some good data set that you can use to make your decision. So loop is still the preferred choice. It has a good lifespan, like generally you have a lifespan of 10 years of loop and then additional 10 years, so you have a 20 years, and by the time of 10 years you are anyway doing the payment desurfacing, so you will reinstall the loops again, right. So the lot of cost is taken care by the desurfacing of the payment. So loops are still the choice. Again, this is totally based on the survey we have done. Camera and the radar are widely used, definitely, but yes, there are issues with them. There are issues with the occlusion problem. Occlusion means when you are viewing from one side, you see one vehicle, but the other vehicle has been hidden, so you can't capture that. So occlusion is a common issue there. But then from the point of, like when we talked to the guys in US, they said, look, we are controlling signals. We don't want to have that accurate value. It is giving us good enough for us to make the decision. That's okay. That's a fair enough comment we have. You have seen that no matter whatever optimization you do in Sidra, Transit 7F, you write your own code. At the end of the day, when you come to the ground reality of implementation, you make your rules and you work accordingly. And as long as the system is working fine, because nobody knows what is the optimal solution for it. That's the thing with traffic signals. As long as people are not complaining, you as an engineer is happy. So they are fine with that one. Hybrid sensors have attracted a very good amount of interest. So the hybrid sensors, like for example, you have a video and radar together focusing at intersection. New products are coming up, because what they are saying is combi of these two can address the limitations of one another. So in the same sensor you have a video camera and you have a radar technology which is getting interest, but still loops are very important. Somebody asked me a question about the cost of the loops. This is what we put that into the public report. The actual report had the cost details, but public report. We put a single dollar for loop because of its cheapness or the very cheap with respect to the buying the loops, and installation cost is well taken care of whenever you are doing the resurfacing of your payment. Cameras, we just put $double. Radar means slightly higher than the loops. Video cameras, due to their maturity, is considered as a cost effective sensors. They are widely used in number of places in US. So if I have to think of a technology for India, I don't see a reason why camera cannot be a good technology, a good source to extract it. However, there is an ongoing cost related to AI and data analytics. A lot of buzzwords happening, AI, and you can do a number of things with the camera. So the technology is okay, the camera is okay, but the backend algorithm will change quite frequently with respect to the various applications. So that should not be ignored, because when you are installing these things, you don't have to say, oh, this technology cost me $10, that cost me $5. No. This cost me $5. I'm just taking the number here, I'm making the number $5, but over the span of my life, how much extra is going to cost me? So you have to consider the whole of life cost for that one. Like definitely the cameras can give you queue length, estimate of the vehicle length, vehicle classification. This is a really great thing. It can even, you can use it to identify the cyclist. You can have the vehicle type detection also on that one. Some technologies even promise to detect the pedestrians in the wait area. When you go and talk to the vendors, we have a 360-degree camera, we can get the whole area observed. We tell you where the pedestrians are, how many of them, and all the information. Definitely there is a marketing stand, and they have that capability to a certain extent, but be very careful in that one. But yeah, this is a very promising technology from their hand. Yes, there was a limitation when with the direction of sun rising and setting, rain, fog, occlusion, lightning, calibration, and all those things. There is a limitation from that angle, which has its own cost. That is for the camera. Same for the radar. Most practitioners who use radar sensor mention they hardly need any maintenance. Video might need maintenance, but they don't need maintenance. Interesting thing about the camera and radar I have mentioned. Yes, they are really rich for the Q length, vehicle classification, etc. But to date, like not to date, whomsoever we have reviewed or we have asked questions, they are using camera as a proxy for the loops. They are using them as a simple loop detector, virtual loop detectors, and a presence type of detection. So just because your system at the back end, your traffic signal control system is working that way, is working on the pulses. So no matter this technology can give you those advanced information with certain accuracy, they are not yet implemented because of that reason. So we need to have some further upgrade in our legacy system, so that these and further algorithms have to be developed that can capture the Q length and all those things. And max pressure was one of them. Like it's not just, you're not just focusing on the pulses and making the cut, you look at the Q length and pressure or whatever from the various approaches. Hybrid sensors give all what these two guys can give. Obviously they come at their own cost, extra cost attached to it, because they have not been tested that dramatically, so that much. Not all the jurisdictions will be happy to just go ahead and pay for that. LiDAR is the most expensive technology among all of these. You put the LiDAR at the intersection, try to detect, but it can give you very detailed information. Its strength is it can give you it is the richest source of information you can have at the intersection. You can understand the safety very well using this one. So it does not mean that you do not have to use radar. Certain intersections with the high safety risk concerns make sufficient use case to implement in that technology. So there is not one sensor for all the intersections. Depending on your need, you decide what sensor you need. Yeah. This one was just some slides to show that how, and Akhilesh has already talked about the video technology, but what I wanted to say was still they are using only virtual loops. Yes, they can detect the box and do all those things, but similarly focusing on and using them as a virtual loops in terms of video camera. It requires calibration. Akhilesh talked a lot on Monday for calibration. It has a capability to track the object, give the vehicle trajectory, and a very good source for the surrogate safety measures at the intersections. Then comes your radar sensors. Basically they are focusing on the vehicle. I mean basically these are, I think the smart micro has their own video on the YouTube. You can have a look how the sensor technology works, and they are basically saying that you can capture a long distance of the stretch and give you more values, right, in terms of Q length, etc. You can get it, and Wavetronics is widely used in number of places in US. Then the LiDAR technology, which is giving you a point cloud and very rich information at the intersection, but at a very high cost. So not all the intersections you might be able, you will not be thinking of putting LiDAR everywhere. It is just certain intersections where you have a better use case or business case to do that. Similarly, active and passive sensors, you can use it to identify, like say the infrared sensors, like turtles. They're at the road pavement. They send the infrared beam. As the vehicle moves, the beam cuts. It tries to make that detection, and so on. So this one was just to give you an overview that look, our legacy systems are there, which are powerful, which are used, and I have given you a number of examples that they are working well. They basically, you don't need like a manual person to control it. They can work in an automated manner that requires optimization, a lot of engineering work behind it, but they are working fine. But they are still not able to fully capture, only focusing on the car. We are not able to fully capture the various other mobility, the mobility of other road users. So, even though our algorithms can be strong enough, if you cannot detect them, you cannot make a very optimal decision. So, that leads to our next discussion, which I asked in the beginning. I use the word next generation. For India, whatever is the first generation, what do you think should be the next generation of traffic signal control? You can ask me first questions of whatever I have discussed, otherwise let us have a discussion of what you think, the one I asked you in the morning. So, for Indian condition, how do you think you can get a good data for the Indian roads?
Most of the intersections are having video cameras.
Cameras, good, yeah. Then what can you do with the cameras?
Image processing.
Image processing,
Like, number plates and how they
They give us vehicle count, they give us the volume, they give us even the mode. They have specific modes.
So, you get a lot of information, like you get the flow modes, okay. So, video camera is what you are saying, yeah, okay. You like let us go to the video camera image. So, you are saying that I can have a camera focused on one intersection at one location, make my virtual loops and start counting the
Speed is also low.
speed. I can get the speed, but intersection speed I will not be much if the camera is at the intersection, then stop line speed is not of interest to me, but yeah, that's okay. You get a speed, you get counts, you get the vehicle type from there, okay, very good. So, you can get the trajectories, you can get the trajectories, good. What else?
With clock also we have in some places cameras. So I think we can find the travel pattern also by using the number plate, like you are using Bluetooth, wherever they are moving the pattern also.
You get that, yeah. So, this ANPR is yes, it's expensive technology to do that, because the ANPR cameras are quite dedicated cameras focusing exactly at a spot, and their job is just to capture the number plate. Whereas these cameras quite often have that zoom in zoom out facility, they are mostly for surveillance purposes. Yes, you can calibrate them and fix them at one location and get the counts, but the moment these cameras are for surveillance purpose and you are zooming in, zooming out and moving around, you have lost your calibration actually, right. So, yes, we have cameras, they are for surveillance. I am not sure how easy you can get the data set from there.
The centralized, like the ITS in the cities, they have specific for counting.
Counting, so you have the counting, okay, very good.
It's there, they have these 5-4 things which they extract daily.
Good.
But how they use it,
But are you able to get the data set? How many intersections you have where you have the counters, camera counters
in Lucknow and Bhopal, I think so there are quite like 10 or 12 currently.
along a corridor?
Not along the corridor, they are selected like high volume areas
Okay.
which they need, or if there has been a previous incidents
Okay.
in those areas. And currently when they were actually converting to smart cities,
Mhm.
so they selected a few areas, high potential areas which they want to convert into an ITS.
Okay.
They want
Good.
to get an ITS system.
Mhm.
And there they started with the basic traffic flow, like data, volume count and mode and all.
Okay.
But how they use that for the
Okay.
we can get the data from
Okay,
the
that's good.
ITS.
If you can get the data for one intersection itself,
Yeah.
so at least you have the traffic volume pattern. You know how many road users have been served over different time intervals. So, if you have have a fixed camera doing it for last 6 months, 8 months, you have a good volume of good data set, volume of data available to you for one intersection. If by chance you have an upstream also a camera you have for a corridor, right. Let us say even if you have it one, you have one good, right. So, you can get that data set.
There are, I think so, 3 cameras for each, like for left, through and
Okay.
for
But but for different approaches, for different intersections, right? You have it for one intersection, you have 3 cameras getting data.
For one lane, like for one way, there are 3 cameras. I think so. Lucknow near High Court, they have 3 cameras for one. So like there were 12 cameras in
Okay.
total for one intersection.
So now let's say you went to that police or whomsoever is managing it. You say I want to have the data set, I can do some let's say study on how we can control signals. They were happy. They gave you 1 year of data counts for one intersection at least. You were lucky you got it for 2 intersections. Let's say you get it and I have given it to all of you. What can you do now? Sorry? Delay, yes. So that if only count is given, it will be hard to get that delay. But let's say you also have a specific stretch of the road captured, and they are also giving you some value of the delay. Because camera has its own limitations how far it can go. So whatever they can give you is a trajectory in that portion. So if your queue is beyond, you cannot get that, right? And generally, if they are using as a counter, they will be using something like this, more or less. So they are basically a kind of a replicating, or they are emulating the loops. So you got a loop counts now, you got a loop occupancy. If you are lucky enough, they might have given you individual arrival and departure, very lucky, or maybe they might have aggregated and given you an aggregated value. But let's say you are lucky enough, they give you the pulse and we give it to all of you.
Be useful for gap acceptance studies. Actually, that is what we do mostly
Okay.
for the gap acceptance studies now.
But if I have given you 1 year data for one intersection, which is a high volume intersection, an important intersection.
Personalized also we also collect. Like with respect
No, I have given you one data now. So that's what I am trying to say. Let's say I got a data from Lucknow. She is an IAS officer. We went to her. We actually bought some gifts for her. She gave us the data. Said, look, go ahead. 1 year data with you. Now given to all of you. What can you do? All of you have the data set for 1 year of
Pattern.
yes. You can at least know the pattern, what kind of pattern you are observing for different time of day of the week. You can know the patterns. From there you can say these are certain profiles I am observing. And because you have the volume, you can at least apply a simple traffic signal control strategy to figure out what should be the green time, red time. At least you can define that, yes, to actually begin with. That can be done. So that's a starting point. I mean, if you think of that intersection can be a fixed time intersection, fixed time control, at least you define different patterns and you can think of having a fixed time control for those patterns to actually begin with. That can be done, right? What else do we have?
Is it possible to utilize public transport bus GPS data
For
signals? Like they will tell us the traffic pattern, how traffic is moving in urban areas.
so bus travel time and your car travel time have some correlation if there is no bus stop nearby. So if you have a link and the bus is moving with the traffic flow, or even if you take your impact of stops out. Let's say even if you have let's say this is the entire corridor with this intersection, that intersection, there is a bus stop here. You know the GPS coordinates. Let's say you have detailed coordinates. You can take the impact of that bus stop away based on the time it is arrived and left, and you can get the average running speed along this one. During congested condition, the other speeds will be certain. There will be some correlation. So higher the bus travel time, higher is your car one. The challenge you will face is buses will be running at a frequency of maybe I don't know 10 minutes, 20 minutes, half an hour. Then you only have that much. Your data will be having that. If it's a high frequency bus route, then you will have more frequent data set. Low frequency, you will have data let's say every half an hour point or 20 minutes point. So that is the challenge you will face. But let's say this is a high frequency route, you are able to get that. Then yes, you can use the bus travel time as a proxy for a car one, but you only get for one approach. You do not know the knowledge of the other ones. So it is valuable, but not giving you the complete picture.
Can we develop any crowdsourcing app?
Yes. Yes, yes, you can develop. Somebody asked this other day. Yes, you can. So, with the crowdsourcing app, what can you gather?
Get the real time data so that we can get the
Mhm.
change in the patterns.
You can do it, but then the struggle you will have there is the sample size and recruiting people who are happy to share their location with you for that time period at the cost of their battery. I mean battery draining. So, people are very much careful about their battery, they turn off their location easily. So, it will be a challenging part, but yes, it can be done, but then this can be done for certain surveys. So, if you are doing some surveys, yes, it can be done, but if you are thinking then it will not be a crowd source, crowd will not be sharing that with you easily.
They are getting some benefit from our mobile app, definitely they will use it.
Benefit should be strong enough for them to
That is my train app is there now, sir.
yeah.
We are getting benefited that there is a approaching the station, everything we are tracking, but they are taking our data, they are utilizing to improvise the prediction of at what time it
Yeah.
will reach the train.
Like Life 360, a very excellent app. I am using it. My family is using it. That's kind of thing. Basically, I know where my family is. Family knows where I am. That's important thing. So you can think of that way. Yeah.
Since the data is there for longer period, we can study the traffic intersection itself, right? If the current signal phases are good enough.
So you study that.
And we try to change that.
Yeah. So that you can do like if because you have a data set and if they are using a traffic signal, you can do your own study and let's say the optimal should be this much, what you are doing is that much. So there is a big difference between the two. Then you can think of running a simulation based study with their signals and your signals and show them that how much benefit can be there. You can make that case, yes.
Like one of the examples we saw in which they had like different for heavy traffic time, this should be this.
Yeah,
should be this.
yeah,
Those can be studied if we have a
Yeah.
yearly data.
Yes.
For that.
Yeah.
We can organize us, optimize the signal
Mhm.
accordingly.
you can do that. That's good. So at least other thing which we have not even explored here is a lot of information you can get from let's say Google based travel time or some other travel time sources, which you can it's expensive to buy, but it is available. Perhaps you can get it from other sources also. If you get a travel time, the crowdsourced travel time information from some third party, that can help you to think of how you can bring that knowledge in your signal optimization. It is not easy because travel time and the demand have a non-linear relationship. Travel time is fixed for a certain while and then starts increasing, and that demand sensitivity, the fluctuation is far too high and it will be hard for you to optimize that way. But yes, a travel time can be a good starting point. In absence of other information, you can use travel time to come up with some smart algorithms with some assumptions, highlighting the assumptions, but then at least a way to control it. As I said, like the people who are using cameras or radars, there is occlusion happening. They might have a side fire camera or side fire radar. They are having an occlusion. They say we are okay. We don't want a perfect. We don't want a perfect observation. As long as my system is working fine, helping me to make an automatic decision and don't need to have a manual person sitting there to do that job because I have hundreds and thousands of intersections. I am happy. So this one actually was opportunities towards the next generation of traffic signal control. I borrowed this slide from the talk I gave in China a couple of months back. You have a network, you have traffic data sources, and basically you want to use the data to have more smart way of controlling the traffic signals. And we have already seen that trajectories are a good source of data. That is one of them. I will skip these slides. Challenge here is accuracy, reliability and coverage of those things, right. Privacy concerns are there. If you give an app, privacy concern is there. Cyber security threats are there. These are actually some of the quite relevant challenges in the developed part of the world where there is quite high amount of data, but even for Indian condition, these questions will be raised depending on how you are collecting the data set. Then so this is on the data side, which hopefully you can handle by acknowledging it, understanding the limitations and doing some part on it. On the in the developed part of the world, the challenge is legacy system upgrade and system integration. So, you have a legacy system that you cannot easily upgrade that one. As I shown you, like I can have, even in US or other places, they have the cameras giving that can give you the Q length or whatever, they can give it to you. System is not ready enough to actually accept, to actually change that. Yes, they are changing the algorithm behind it, it takes time. So, that are the selected challenges that you see here. So, our current system is right now here. I am talking more from the Queensland perspective. There is a lot of papers you will find in V2X for traffic signals, vehicle to infrastructure communication, and you can use it to control traffic signals. PhDs are happening in this space, and to certain extent, yes, some intersections you are sending the information from the signals to the road users, to the drivers about when the signal is going to change. Things are happening there, but can I use V2X to totally control my signal? I do not know how long it is, 20 years, 30 years, 50 years, I do not know that. So, it is a bit long. Near future is from a fixed base, at least there is a lot of interest to actually go towards the movement base in Queensland for a certain point, because for last 50 years they have been using fixed base, and when you do something there is a cycle to change to another one, and signal controllers have their own life cycle, like lifespan. When you are going to make an upgrade, you want to make sure that you are ready for the future. That is one thing, but from intrusive technology, more and more these technologies are going to be advanced or more mature, more accepted, and you will have more and more data available, and the multimodal is the most important part there. So, the near future in my view is this, focusing on, I mean, algorithm point of view we are ready, there are a lot of scientific literature there, but data point of view we are not, and more sensing technology might emerge for that one. That is again the next generation. Currently you are a detector based and traditional approach is there. Scientific literature you see, they have even talk about signal free system. They say we have autonomous cars running everywhere, you can give you a slot at the intersection, move. A lot of papers are already published in IEEE or some other journals, connected autonomous vehicles, but these are long future. Good for the papers. Connected vehicles might add some value. There was a lot of paper in terms of how you can use connected vehicle and make a system totally detector free, make your control just using connected vehicles. We have shown some sample recently. It can help you to do some performance measures, help you to improve your understanding of how your system is behaving, maybe more about health monitoring. But the next generation is somewhere moving, slowly moving. You have an incremental increase, you just keep on moving. So, whatever step you have right now, whatever way you are controlling right now, you make it better, you do not change it overnight. So, that is where the practitioners, or that is where basically the things will head. So, if you are working on a signal control, figure out what is the current step, how we are doing it right now, can we make the process better, can we make it more smarter based on whatever knowledge I have. So, that was for the next generation. Yeah. Now, so somebody asked some other question during the break to me. This one was with respect to the data collection itself. Is it you who asked the question? Who was the one? Data collection. You mentioned about the cameras, right? We have so many cameras, but you also mentioned about the benefit you can have just before onset of congestion. What was that question? Can we?
Signal when we approach early, before approaching the peak hour, really cut off. If we make sometimes other signals will be red, the green approach nozzle it will be empty.
Yeah.
We can see. So if we break that,
yeah.
then it can be. We can avoid especially in
Yeah.
because signals are fixed.
Yeah. So, the point he raised was early detection that we are talking about, right? Sorry, early cutoff. If we have a fixed time signal specified, but during the early morning time period when the demand is not properly distributed, if I can have some kind of sensing technology that can detect the presence or demand in an approach, and I am able to make an early cutoff, I will be able to reduce my starting the initial delay, or I can delay the onset of congestion, because traffic have to necessarily stop a lot in the area where actually you are from, that because of the way the signals are designed. Yes. So, there are small measures that can be done to actually improve it. Yeah. So, that is more from the practical perspective. From academic perspective, what do you think you can do to improve the the research in the area of signals? We have a IRC, Indian Road Congress traffic signal document that specifies how the signals should be designed. We have a heterogeneity of traffic over the road network. You have seen that even if I give you the demand, you want to optimize the signal timings, you might be using some software, like say the SIDRA for example is a very well accepted. Can you use this straight away for Indian condition? If not, what research you can do to actually make it better? Think from that angle. Your heterogeneous traffic condition has their own characteristics. So, I said do not worry about the site friction, heterogeneous will be there. Think about what delay equations can be there that can help you to get a better delay values based on your heterogeneity of the traffic, and that can be utilized for optimizing the traffic signals. Signal phase design, what phases should we be considering for the Indian condition? We do not need to have that complex phases, a simple phase approach that can make the road safe and our road users can understand, and that can help for us to improve the like make it more automated. Coordination, the corridors, which corridors I should be focusing on? Like if you have, I mean if you can think of like for example, the bus data will be helpful to study the entire corridor. So, all the data set that you have available to you in whatever form, bring them on one platform, understand the data source, how you have collected the data, you understand the data source, and then say now this is the knowledge I have about my network. It's an imperfect knowledge, limited knowledge, but I am a traffic engineer, I know how the traffic behaves. In fact, I am one of the agents in the road network also, so I know how people drive. Can I make some inferences, can I make some models and assumptions, so that I have understanding, I can figure out how my network behaves. So, those things I think can be done to have good understanding of the system, and then you can think of improving. Yeah.
Coordination, signal coordination. So, any two signals if we take, if they are close enough, we can coordinate it. But is there a threshold, like sometimes it can be counterproductive also?
So, threshold means how far, how close they should be?
Not in terms of distance, but in terms of demand.
It is this, yes, it has to have a high demand. It is not that you are always going to coordinate them, no. There should be a justification that there is a high amount of demand going in this direction. So, I should be coordinating them. So, generally it is the corridor, like say example quite well connected towards a CBD. I mean if you have a center business district or some other area, or let us say airport, I know a high volume is going in this direction. So, it is better to just flush the high volume. You can even think of other way, hold and flush, hold them at upstream, you know that these are going very fast, or they have to go in this direction, hold them upstream first and then flush them. So, you can let them queue there, but then you can flush them. So, different strategies can be applied, but coordination will work fine only when the intersections are close by, because as I mean we have a term called the platoon dispersion. So, let us say if these guys are moving in a platoon form, if the length becomes longer, this becomes they start dispersing, then the whole benefit of coordination has gone. It is quite natural that this will be drive a bit faster, and these might be they just keep on slightly spreading. But if they are so close to each other, you do not have enough room to disperse. These guys will move, and you can have the whole band going to go through. I have so many other things to cover. I am only focusing here right now, but yeah. Okay. You want to take a break for 10 minutes and we start after that? is okay.